Oh, getting a lot of light from that window. That's better. All right, now we just have the natural light of the twin suns of Tatooine. Good morning, QED coders. We should be seeing Jan here pretty soon. I'm looking forward to sharing with him some of the improvements that I've made to Jinaga.JS over the past week, based on what I saw when porting the ImprovingU application. Good morning, Jan.
I'm late. Sorry.
No. Actually, 2 minutes early.
Yeah, but you were first. Yeah, and on top of that, I'm feeling a little bit sad and annoyed
Oh,
that it was 2 weeks and I almost made no progress.
oh no.
Yeah, so there was always something. There was always not enough time. And historical
Yeah.
modeling has to progress. I really have to find a way to, yeah. So it's always something exceptional, but there's always a reason not to make progress. But I did manage to see your YouTube from last week.
Okay, good.
Yep, and
So,
it's like a thriller.
yeah.
It's really okay. Yes, he has 3 problems. What is the solution? And the first one gets solved, but the 2 others, I guess you solved them.
I did. I've got updates on all 3, and as you might expect, they're not unrelated to one another. So yeah, let's dive into that. So to kind of summarize, the 3 problems were, first of all, I found that when switching to the managed Postgres database, that things were taking longer, and when I looked at the telemetry from the managed Postgres server, it said that the queries were extremely fast. So it's like, okay, the optimizations seem to be working, but it's still taking longer. What's going on? Problem number 2 is that the ImprovingU application is pretty inefficient in the way that it runs its queries, and so it's got a lot of queries going on in parallel. And problem number 3 was the way that I was dealing with timeouts. It didn't seem to do a retry. So,
but the number of queries is improved in the React framework, and once we get to the projections in Jinaga with the link, that should be okay, if I understand.
Yes, that is correct. So first of all, the explanation for why things are taking longer, even though the queries seem to be faster, is latency. So when running on a virtual machine, the machine is always running, and it's always immediately available. Managed Postgres database, it's a shared resource, and so Azure is doing some resource optimizations there to make sure that everybody can share nicely, and that means that each individual request just takes a little bit longer to get in the queue, to get processed, and then get back out.
But does that mean that once you reduce the number of queries, that the problem is solved? Because if each query has a little bit latency, but your query executes in about 20 milliseconds. On the client side, you measured about 2 seconds or even 5 seconds, which give you a timeout. It's even a very big difference.
Yes, it is. Yep, and that's precisely what I saw. So I fixed that first by changing the way that I'm managing timeouts. So I did find that that I was doing two different types of timeouts. And when I went back to it, it was like, oh yeah, that made sense that I was doing it that way. So for all of the write operations, actually there was just only one write operation, that's save. So this is coming from the top level. Save was put inside of an exponential backoff retry, so that and this is on the client. So the client itself is so within the browser, it's saying, no, I really do want this data to be saved, and then just repeating that query. I didn't have that same exponential backoff because my reasoning at the time was the user is already looking at some data. This is just getting fresh data. They can they can tolerate having some stale data for some period of time. But I hadn't really considered that this might actually be the first fetch, and so there does need to be some retry. So for that path, I did an exponential backoff that just stops after 3 attempts. So the save still has to persist, but I didn't want that same behavior for retries. Just slamming the server while you're in a tunnel. So that that change just on its own allowed it to continue, and the primary reason that it was a problem is because of HTTP 1.1. So in HTTP 1.1, a browser will open up to 6 concurrent connections, and then any other XHR requests that you make after that will block, waiting for one of those 6 connections to finish, and then it'll take it and it'll continue. So you can actually see in the waterfall, all of the queries that I was issuing all at the same time were all starting at the same point, and then 6 of them started immediately, and then as they finished, the next ones picked up. But because there were so many, and because the latency had just now increased, the ones at the end were exceeding the 5 seconds. And by the way, the 5-second timeout is one that I had put into the client by default.
Yeah. It might not have to do also. No, it's not in .NET, but if you're asynchronous, remember last time with the SQLite, if we were just using tasks and not real threads, we had this task scheduler, which only allows in default configuration, I think 6 or 8 tasks at the same time. And the others were delayed.
Yeah.
It's not perhaps the same issue we are having there.
But yeah, you're right. It is a related idea. Yeah, I was just talking to one of my friends about it was just a completely unrelated problem that he's trying to solve. This was a Node application that's spawning a separate process, and then he's reading data from a file that this process is writing, and the process says, okay, I've finished, and so he stops and he says, I don't get all the data. I said, well, there's no guarantee that you're going to get the signal from the process and the signal from the files in the correct order, because those are 2 separate channels. And I said, well, that's kind of similar to what happens in Golang with coroutines and channels. Is you have to end a Go routine on a signal received from the channel that Go routine was set up to read. If you try to end it because of some other channel, you'll get things out of sync. So it's the same ideas pop up in different contexts, and they're always the same idea. So yeah, I think this is another one of those cases where it's the same idea. We've got a limited number of concurrent asynchronous requests, because JavaScript is single-threaded. All of these are asynchronous requests. but the way that you manage them, if you manage them intelligently, then you can tolerate that. And so I think there are several different solutions to this particular problem. So solving the just doing a retry on timeout and putting a random delay in there as well. So I don't just wait for 1 second and then try again. I wait for 1 second plus random up to a second. So between 1 or 2 seconds, then do a retry, and then between 2 and 3 seconds, do a retry, and then between 4 and 5. So it staggers the retries, and so that means everything pretty much just makes it on the second try. So that got past the issue, but there are two other ways to solve that problem. One is to just switch to HTTP 2.0, which offers many more concurrent requests, because it multiplexes those requests on the same socket connection. And I actually did go down that path a little bit, but didn't quite get it working. You have to change some things in the server side. Express, just out of the box, uses the regular HTTP library that's built into Node, and it doesn't support 1.1. There's a different library you can switch to. I tried that out. I still wasn't getting 2.0 behavior out of it. It might have been something I was doing on the browser side, because the browser is still using XHR. It's XHR rather than fetch, and I'll talk about that in a little bit too. So couldn't quite get HTTP 2.0 working. So that's still something I want to do in the future, but I don't want that to be the only solution, because you can't, at this point, 100% rely upon 2.0 being supported everywhere. There's some, I think even by default now, with Azure, if you stand up an app service, by default it's still 1.1. You have to go in and switch it to 2.0. But so that's one option, and it's still on the table. But another option that's also on the table, and I haven't implemented yet, is to do with the XHR versus the fetch. So XHR, XML, HTTP request is the old browser object for making a request. There's a new one for that's called fetch. It's called fetch whether you're doing a get or a post or a put. It's still called fetch. But at the time that I started the Jinaga project, fetch was still pretty new, and it did not support timeouts. So there was no way that you could say you want to timeout after 5 seconds. And I was like, nope, I have to have timeouts, otherwise you can't detect network partitions. They'll just keep on going. So I stuck with XHR. In 2020, they added support for timeouts, but not in the same way as XHR. You can't just simply say timeout after so many milliseconds. Instead, you provide something very similar to in .NET, a cancellation token. They have a different name for it, but it's the same idea. You create one of these things, and then you give it the signal, and then you keep the thing, and you tell it to initiate the signal. And you create a different one for each request that you make. And the code examples that you see online are create one of these things, start your fetch, and also do a set timeout and signal it after your timeout is done. So it's a very simple way of re-implementing the same timeout behavior that you get in XHR. But you could also be more intelligent about it. And so the way that I'm thinking I want to use that is that rather than have a single set timeout that or a set timeout per request, I want to have a more intelligent timeout state machine that is it knows, are there any other requests currently in process, and only if no other requests have returned within the 5-second window do you then signal the ones that are currently active and say, okay, time those out?
Okay, because then you are sure that there is a partition in the network.
Yeah, exactly. And you're not just waiting in a queue.
Mm-hmm. Okay.
So, but yeah, that when I saw that behavior, I was like, well, that was not expected behavior for the timeout, because I thought that the timeout would start at the time that XHR actually got to the head of the queue and initiated its connection. But that timeout starts when it gets into the queue. So basically, with these tokens, I'm able to simulate kind of almost that behavior.
And that was the 5 seconds timeout that you experienced?
Yes.
Okay.
Yes. Yep. So in Jinaga, when you say I want to create a browser, or Jinaga browser.create, that option structure that you give it, you can specify an HTTP timeout, and I use that HTTP timeout in XHR. And I default it to 5 if you don't specify anything. 5 seconds.
Yeah.
Yep.
Because you were
have
thinking
to specify
during the presentation.
Yep.
Yeah.
Yep. And I actually found that code 3 seconds after I hung up. I was like, I really want to see this before I go to work. Yeah, there it is. Okay. Should have just looked while I was on the call. Yep.
Okay. So we had this timeout behavior, then the queries, but the queries, they really, there's so much difference. I find it still amazing, because we are talking about a factor 20. Yeah. If you run it in 20 milliseconds, and sometimes you had more than, what was it? More than, more than 2 seconds, more than 5 seconds even. Yeah. So we are more than a factor, factor 50, factor 500.
Right. Yeah. Well, yeah. So yeah, the latency is significant. I was seeing with the virtual machine, what I was calling the longest running queries, they weren't actually the longest running queries. They were just the ones at the end of the queue. Those would get up to about 250 milliseconds with the virtual machine. So there's still some latency with the virtual machine, of course, but yeah, switching that to managed Postgres, that was enough to push those over the 500 millisecond mark. So yeah, if you just a little bit more than double the latency going to managed Postgres, that causes that problem.
Okay, that's why you were seeing a delay on the virtual machine, because I thought the presentation itself was on the virtual machine, but you said I don't manage to have timeouts on the virtual machine. I think most of it was about 2.5 seconds, and the moment that you put it in Azure, there you get from time to time more than 5 seconds.
Right. Yeah.
Is that
correct? Yeah, that's correct. Yeah. So it's still saying up to 2.5 seconds on the virtual machine, over 5 seconds on managed.
So even on the virtual machine, we were having a lot of latency.
Yes, and I just kind of chalk that up to network latency, because it's running in an Azure web application, or Azure, what do they call it? Web service. Yeah.
No, the virtual machine was running locally, no?
No, the tests that I was the test that I was comparing it with was ImprovingU with the database running on a virtual machine, but that means the node application is running in an Azure app service, and that app service is connecting to Postgres running in a virtual machine. So there's still a network in between them, and then just moving that database from virtual machine to managed Postgres, that just increased that latency. So
I thought the whole thing was running on your own computer with a virtual machine on your own computer, but that was not the case.
Right. Yeah, I didn't use that one as a benchmark because I didn't think that was Well, not for this particular test. I did use that as a benchmark when I was just testing the SQL, and with just the SQL, I saw that, and that's those are the numbers that I reported. The inserts were about the same. I was expecting the inserts to be a bit slower, and the load was much faster, and the queries were, I think, were about the same as well. Yeah, and I was expecting the queries to be a little bit faster because of the integer foreign keys, but they turned out to be about the same, and that was all just locally. So there, I was just looking at the query performance and eliminated all of the network performance.
But that means that in .NET, in the application I want to build on the mobile phones, that we will not have a lot of troubles with this issue, because actually the real-time performance is between the application running on the telephone and talking to the SQLite database on the same telephone.
Right, yeah.
It's only the moment that he makes a network connection to the server, but all that is asynchronous and in the background. So
right, yes.
We should not have too many problems.
Yep, exactly. And in fact, for the ImprovingU application, I intend to turn on the local browser storage using IndexedDB. And so I've had that feature in Jinaga for the longest time. I've demonstrated that feature. It's all working. I just never turned it on for the ImprovingU application, and that's primarily because I'm using the ImprovingU application to test the load on on the server, and I didn't want to hide any problems. So yeah, using my friends as guinea pigs, but they know that I'm doing that. So
I'll be happy to be guinea pigs.
So even now, it's not turned on. I was thinking maybe I should turn it on this weekend, but no, I decided I'm going to collect another week's worth of telemetry, make sure that this has solved as much of the problem as I can, and then I'll turn it on next weekend, and then everybody say, whoa, this is just so much faster. Well, yeah, because it's only hitting your local browser's database.
All right. Then I also saw there was an additional endpoint you could set up when you do create a Jinaga server.
Yes, that that works really well.
And actually, what was that doing? So you had because it's not your local database, it was your server database that you had connected, and then you go to another database, which was the 2.0 version.
Yeah, so
over the HTTP endpoint.
Yeah, so the way that worked is that so the browser is still hitting just one HTTP endpoint, and the way that I had it set up in that particular demonstration was Node running on my own machine. So the browser was configured to talk to local hosts, and then the server running on my machine was connecting to its backend database, which in this case was managed Postgres. And then the HTTP endpoint I configured for the server was the deployed application for ImprovingU. So it was talking to the backend running in Azure, and that backend at the time was still on Jinaga 2, and it was connected to the virtual machine for its database. So we've got browser to local node and managed Postgres to remote node and virtual machine. And so every request that the browser made, the local node application would serve that request from local database and send that request over to the remote node application, which would then serve it off of the virtual machine and pull that data in, and it would save it to its database, and then it would also return it to the browser. So that set up a replication path So every piece of data that I looked at from the browser was pulled from the old database and copied into the new database. So all I have to do is navigate through the entire application or write one query that pulls everything, and then everything will get synced up.
The old database was 2.0, the new database was 3.0. But so the Jinaga model was exactly the same in both. It was only the database structure, the indexes, the integer indexes, the recursive processing that had been replaced by extra tables.
That's
that
correct,
was the only difference.
That's the only difference, yes. Yep, the model was still the same.
Because the same system could be used to upgrade a model.
Yes.
And that would be great in the future.
Yep, and the same system can be used to archive data. So you take your running database and your running server. You say, okay, that's now the back end. Stand up a new one, point all of the traffic to that one, and it starts copying today's data. But last year's data, nobody's querying that. So eventually, put that into cold storage. Keep rolling it back.
Yeah. Okay, that's a very nice idea. Yeah, a little remark that could improve the presentation. And I just reminded 2 minutes when you were talking about the different databases, having a visual overview, a diagram would be great. And what I missed in last week's YouTube was just the visual presentation of the model.
Oh, right, yeah. I wasn't even concerned about the model. Yeah.
Yeah, because you have it in your head.
Yeah.
But somebody who's watching it, you went through the queries, and then you say, okay,
right.
that's a successor and that's a predecessor. and I was thinking, where are we going?
Yeah.
Well, if you have the model next to it, then you can just follow.
Yeah,
just
that was just a string of S's and P's.
Yeah.
It's like, oh,
yeah, but it's for somebody who doesn't have the model in his head. It's something weird is happening.
Right.
But I think if you see the model next to it, it would be much easier to follow.
Yes, indeed.
Then you ended with Merkle Trees.
Yeah. That was just something that kind of popped into my head that morning. It's like, oh yeah, I really want to explore that.
So my immediate reaction, go to Wikipedia. Oh, what was it again? Okay, all the hashes. But then I'm wondering. So if I understand well, the purpose is that we give a definition of the Merkle tree that should be used to compare all the facts in the database.
Right. Yes. So let's see if I'm trying to think. Would a diagram work well here? And could I whip one up real quick? But so we'll just try this as fingers in the air first. So a Merkle tree. The idea is that let's start at the leaves of the tree, and I mean, that's not the way the algorithm works. The algorithm actually starts at the top, but we'll talk about the leaves first. So you have some information, I have some information, and we've got all of these different pieces of information that we have. You could think of them as git commits if you want, because each git commit has a hash. And so you say, oh, okay, I've got a commit that's got this hash, and I read it out to you, and you just look in your database. No, I don't have it. Send it to me. We do that, compare a bunch of hashes, and so we end up sending just basically all the hashes that we have, and you send all the hashes that you have, and then we say, okay, now narrow it down to just these. So it's a pretty big initial payload to figure out what data you don't yet have to do that synchronization.
Can you compare it to a binary search?
Right.
Where you say we just start in the middle and then again the middle to search faster.
Oh, okay, yeah.
You have a line, a chain of values.
Mm-hmm.
You need to find a certain value. You can say, okay, I compare to the first one, to the second one, to the third one. You run off the whole chain until you find the correct value. What you can also do is just sort the whole chain. You have the smallest one here, the biggest one there. You say, okay, is my value that I search, I go to the middle, is it smaller or bigger? Is it bigger? Then it will be here. If it's smaller, then it will be here.
Mm-hmm.
So the next step, I have the half, again, the middle, bigger, smaller, binary search.
Yeah.
And that Merkle tree is a little bit the same thing, where you search for.
Well, it's
Um,
it's different in that. Um, so I think the binary bifurcation of that hash space could be one way to build a tree. Um, but that's not the only way to build the tree. And and I would expect that even if you have just a small number of differences, because hashes are kind of randomly distributed. If you said I've got three facts that you don't have, and I stick them into my sequence of hashes, then when I take my first half, it's going to be bigger or smaller by one fact than your first hash and your first half, and therefore there's going to be a difference. Um, so so I think that that would save you something over just here are all the hashes, but it would not be quite as efficient as a different way of figuring out how uh, to build that tree. So so yeah, the Merkle tree algorithm doesn't really tell you how to build the tree. So ordering the hashes could be one way to do it, but if you've got a way to take a bunch of those pieces of information, we'll go ahead and start calling them facts. You take a bunch of those facts and you group them together, and then you hash all of the hashes, and you say, I've got a group that has this hash. Do you have that group? And if you have a group with the same hash, then very likely it's the same set of facts.
yeah,
Um, and then now you just make groups of groups and groups of groups of groups and build your tree up to the node to the top of to the root. And now you can start your conversation with my root hash is this, your root hash is that. If they're the same, you're done. But if
and
they're
we
different,
both have the whole tree, which
yeah,
is identical, all the facts.
yeah, exactly. But if they're different, then you say, okay, let's go down one level. I'll list out the second level hashes. Oh, these are all the same. Ignore those entire chunks of the tree. Let's just focus on the ones that are different. Keep on going down, and we'll find in login time, uh, login initial communications, which facts are different. So the thing about a Merkle tree is that it works on trees, and Jinaga just by itself, or historical modeling just by itself, works on directed acyclic graphs. A tree is a directed acyclic graph, but not all directed acyclic graphs are trees. So if I were to just naively say, here's one fact, and I've hashed all of its successors, um, which is the opposite way that I usually do the hash. So if I give you the hash of a fact, it includes that fact's data and all of its predecessors. So I'm concerned about the transitive closure with the upward facing cone. This one, we're looking downward because we want to add new information that we don't yet have, so it's not in the transitive closure. Um, so so if we were to say here's the company fact, and I've hashed all of the successors of the company, so that's all of the offices, and I've hashed all of the semesters, and I've hashed all of the catalogs, and then the courses, and then the registrations for those courses, and go down the tree. I'll end up including some facts in both of those. So this course was in this office, but in this semester. So it ends up in both of those areas, and so you get a less efficient Merkle tree. You'll detect those new facts in more than one branch.
Yeah, but Michael, if you start from this fact here, and then you have the successors. And you want to see whether any successor has been added. That means that the difference between this Merkle tree, my Merkle tree, and your Merkle tree will probably be, or will always be, in one of the leaves.
Mm-hmm.
But that means that you have to walk through the whole tree to detect that something has been added.
Yeah.
And the efficiency will be much higher if something on the top changes.
That is true. The thing that you're saving is the fact that walking down a tree is a much shorter walk than walking across a tree. So as you go down one step at a time, you get to eliminate a bunch of things that did not change, and so you can. So yeah, there was a course added to to the current semester in the Dallas office. So you're looking at the Houston office, and same hash, nothing has changed over there. So you get to ignore all of Houston's courses.
All the branches, that branch, no problem, and you walk down to that particular leaf that has changed.
Yep.
Yeah.
Yep. The problem is, and still sticking with that example, this is a new course in Dallas for the current semester. If you're just naively looking at all successors of the company, the semester is a successor as well. So you say, all right, the spring 2022 semester, there's a change. So I have to investigate that. Well, I'm already investigating it because it was added to Dallas.
Yeah.
It was the same fact, and that fact has two predecessors that then come back together at the company. So basically, I could just build that naive Merkle tree search into the library without knowing what your model is, and I'll get some benefit from that. But if I can get you to express a projection, as if you were going to render this on the user interface as a tree. You just express a projection, and then you would say, okay, for this projection, I'm going to, maybe you'll say I'll put semesters first and then offices second, even though every semester is going to have the same set of offices. I order them that way because I happen to know in my particular model, you tend to add things to the current semester and not to old semesters. So I get to eliminate all of those old semesters very quickly. And then it'll usually find just the current semester has changed, and now we see which office. And then, it's usually just, between one merge and the next, it's usually just one office, and then you drill down. And so you get to, if you do this quickly enough, and there's only one course, for example, that's added between runs, then you will quickly walk down the tree, and you'll go down to just, there's that one office, there's that one course, here's the title, and so you quickly find your way just to the facts that have changed.
And what if, for example, you have a course which has a predecessor semester and a predecessor office, Houston office, first semester?
Yeah.
If we know in the model that course always has a semester and an office, it's always there.
Mm-hmm.
Then we can say in our Merkle tree, for example, we don't consider the link to a semester. We only consider the link to the office,
mm-hmm.
and then it becomes a real tree.
Yeah. So so those are two different ways that you could describe that tree. The way that I described it, I kept the semester in, and I just deliberately put the office underneath the semester. So I wasn't ignoring the semester, but I was putting that higher in the tree. And that was because I knew in my model the semester was the period. So by invoking the period pattern, if you put your periods as high as possible on that tree, then you get to take advantage of the fact that old periods have less activity, and you get to ignore more things earlier on. Whereas if you don't use the period at all and you just go straight to the office, then by the time you recognize all of these offices are the same but Dallas is different, then now list all the courses. I'm listing all the courses throughout history, and I'm giving you a lot of hashes on that level.
Yeah, that's true. So you better filter out by the period pattern.
Yep. Yep. So it takes some knowledge of your model in order to get an efficient Merkle tree.
But then why use this Merkle trees? Because if I understand well, in your presentation you said then we can see whether we almost have the same trees.
Yeah.
But the purpose finally is to have exactly the same trees, or
Right.
the way is just to speed up the comparison.
Right, exactly. Yeah, it's just to speed up the comparison. The way that that I'm the way that I'm currently doing the synchronization is the least efficient way. So the node, every time it receives a query, it just sends that query to the to its parent node, and that parent node responds with a list of hashes, and then it says, oh, I already have these, I don't have these, so now load those hashes. So so it's basically doing that that string of hashes. So the very first time that you spin up a node and you say, here's my parent, here's the first query, give me the hashes, I don't have anything, give me back all those things. So it's the least efficient way of figuring out what needs to be synced. But the way that I was thinking I would move toward would be using the date learned. So so anytime you write a fact to the database, you also capture the date that this particular node learned about that fact. So that's not the date that the fact was created on the client. That's just the date that this node learned about it. And that orders facts sequentially per node.
Yeah.
But facts don't have a sequential order globally speaking, but they do have a sequential order per node.
And there we are back to the pointer that we had in, what was it? Correspondence, I think?
Yep. Correspondence had the bookmark. Yep.
Yeah, the bookmark. That was the term we used for it.
Mm-hmm.
Indeed, if you have a bookmark with the date that the server learned about that node, but the disadvantage is if you have two different servers, you still have a bookmark per server.
Right, exactly. Yep. Yeah. So if you're doing peer to peer, rather than directly talking to this is my one parent node, then bookmarks are going to guarantee that you're going to do twice as much work if you have two peers, two parents. Yeah. You're gonna say, yep, got those. Oh, I already learned about those from this other parent. Okay, here's some new stuff. Oh, I already learned about that from this other parent. Here's some new stuff. But Merkle trees will be a more efficient way of doing that for the peer-to-peer distribution of facts.
Okay, that might be another way of looking at it.
Yeah. Yeah, and anything that I can do to avoid using a linear sequence, that just makes me happy. It's like if I could just completely get rid of any linearization, any serialization, that'd be fantastic.
Because actually, a linearization is a local thing, so that gives trouble in a distributed environment.
Yes.
Okay. There was still something I was thinking, because we were always using async tasks, also in the saving of facts. Is there not a risk, Adam? Because I don't remember, because of course we are using predecessors and successors, so the ordering is in this predecessors and successors.
Yes. So there is a partial order.
Yeah.
And so.
But I do remember, I think it was in correspondence, at a certain moment, to have the facts in the right sequence. Fact comes in, and we would say if the predecessor is not in our database, then we just put it aside until the predecessor comes in.
Yes. Yeah, there's the topological sorter. Yes.
Yeah. And so I was wondering if you are using async and await for saving facts, then we might have a later fact which gets saved first.
Mm-hmm. Yep.
Is that not gonna give troubles?
Yes. Let's see. Because I know I wanted to talk about this kind of behavior. So I'm just trying to see if I've already got the code up. Yeah, it's not quite there yet, but I can get there quickly. All right. Okay. So now I'm trying to find the right view. There we go. Okay.
Yeah.
Yep. All right. So here is Jinaga. Here we're looking at the server connection. So if I go into wait, no, I'm sorry. That one is ImprovingU. There's Jinaga. Okay, yeah, and there's the default 5-second timeout.
Yeah.
Yeah. So if we go into Postgres store and we hit save.
Save routine.
Yeah. So we get just an array of fact envelopes, and we're hopeful, but we're not expecting that these facts are in a topologically correct order, meaning that within this array, the predecessors appear before their successors. And so we have insert facts, and this one, or maybe it was. Yeah, I'm trying to remember where I did that. Maybe that is actually part of the protocol, that it has to be topological by the time it gets to the server. That doesn't. Well, oh, okay. It's not really by the time it gets to the server. It's by the time it gets to the store. There's another class in here called. Where is it? Here's a topological sorter. Okay, there it is. And so, yeah, this takes an array of fact records, and then it's going to call you back on this map function in a topological order. So, yeah, this is doing that algorithm that you just described, where it's got the facts received, and if it's looking for a predecessor that you have not yet received, then that gets shifted onto the waiting predecessors. And then once you do receive that predecessor, then at that time it grabs it and it runs it through. It's got to run it through the map at that time. Maybe it's already mapped it. No, it has to call map in topological order. Yeah. This code is a little bit hard to read on the fly, but it is well tested. But yeah, so we run it through this topological sort, and then we basically receive each fact record in topological order along with its predecessors, and these are the results that you returned from map when the predecessor was called. So if we see where that is referenced,
reference for every fact that is saved.
Yeah. So like actually, here's one place that I have been in this past week. We run the topological sorter on this set of facts that are coming in order to do the authorization. So the map function that we come up with is this little function right here, which calls this .visit. So this is basically the map function. This is executed in order of the facts as they should be if they were predecessor first. So the very first one that you get, it's going to have a top level fact record. The set of predecessors for that fact is going to be empty. And so this is going to run the authorization function for that top level one, and then figure out if if this particular logged in user is authorized to give you that fact. And it's okay if the root is one that the user's not authorized to give, because it might be, like, for example, the ImprovingU company, and it's only the creator of that company that is authorized to actually issue that company. And so here it's checking to see, does that fact already exist? Do I already know about it? Which means somebody else asserted it and they were authorized to do so, and so therefore I'll go ahead and allow it. But if it does not exist, then either they're authorized and this is a new fact, or they're not authorized and this is forbidden.
Yeah.
But if we do know about it, then if they're authorized, we sign it. If they're not authorized, we just say, this is an existing one. We don't attach their signature to it. So yeah, this is one of those areas where we do the topological sorting.
So it is important to keep this topological order when we do save to the database.
Yes, right. Exactly.
And then I had one thing I was running in. Remember, I made a lot of tests in the context of this SQLite database. I was cleaning up the tests a little bit, but then, for example, at a certain moment, perhaps I can show you.
Okay.
Make it smaller first, so that it is readable. Screen. Merkle Tree. Where is the? It's here at the bottom. Jinaga.net. Yeah. Is it visible like this?
It should come in. Yeah, it's looking good now. Yes.
For example, in this connection factory here, where was it? I had this logging class. Yeah. I wanted to use the output of the tests. So that the test framework gave me the possibility, if you run a test in the test explorer, to get the output here. Yeah. And so I could write whatever I want to this output pane every time I run a test. But then I wanted to have, for example, feedback from a connection or from a transaction. And that's where I had this public static string, mylog. Let's see, where did I have it? Yeah. Actually, I had two. So I had a connection log. I called it connection log, or I had mylog. I added comments to it, diagnostic data, and then at the end somewhere, for example, if I take connection log, I was feeding it back. Yeah, I was feeding it back to my log, and then my log was going where? Not here. No. Oh, yeah, my log was a public static variable that I was using directly there somewhere. Yeah, here, for example, output connection factory.mylog.
Yeah.
Within a test, yeah, I am doing the same in this test here. Output. So,
and were you finding that under concurrency you were sometimes missing entire transactions worth of logs?
it went quite well, but there were certainly threading issues in the logging.
Yeah.
Now, the issue is in production in the connection factory. I don't want to add all this logging code.
Yeah.
But I would like to keep it in the tests. Of course, I could use a compiler if then, and just with a compile variable, leave out the code. But then you have two different sets of code. You have your production code, and you have a code that you run during testing.
Yeah.
While the purpose of the testing is to test the production code.
Right. And so you don't want to change the production code.
Dilemma?
Right. Yeah.
What is the best practice there?
Yeah. I could see two ways of doing it. One is to inject into the constructor a logging receiver, and then in production, actually it might make sense for you to still use a production logger, but just at a debug level, so you can have it turned off most of the time, and then turn it on in production when you need it. And then in test, you basically implement that with a string buffer, a string builder, and then do the right thing with it. So that's one. So injection is one way to do that. Another way I could think of is an event. So every time you want to log something, you just fire an event, and then whoever has the connection factory can just subscribe to that event, and then do one of those two things.
Yeah, and if you don't have a subscriber, then you don't raise the event.
Right, yeah. Yeah, because you're using question.invoke.
Yeah. And that's not going to cost a lot of CPU cycles in that way.
Right.
Okay, that might be a clean way to solve this problem. Because I like to keep it in the code so that we can rerun the tests in a full form.
Yeah, I agree.
Even if it's not completely thread safe. Now we might also add some locking around it, but
yeah, I do like the idea of logging in production, and that of course I would want to be thread safe. But yeah, if you just use like a log for net, you're going to get thread safe logs. It's already knows how to do all that. Or actually, now the Microsoft.logging NuGet package is a good solution to that as well. Is that a NuGet package, or is that already? I think it is a NuGet package. Yeah.
I will find out.
Yeah, but yeah, even in testing, I think it would be not too much extra work to make this a thread safe logger. So yeah, you could just in your event handler, you can put a lock around your your string builder. Yeah, string builder on its own is not thread safe. There might actually already be a thread safe. Yeah. Just do your own locks on it. It's fine.
Yeah. Anyway, because if you put locks on it, then we could get into one or the other deadlock, and then but in that case, the test will take a lot longer, and we might make it fail in that case.
Yeah, I think you
so
would.
if something goes wrong.
I think you would only get a deadlock if you entered the lock and then you did some other reentrant action that could take another lock. But in this case, you're entering the lock, you're appending to a string builder, and then you're exiting the lock. So
Yeah.
so the dependencies of the locks only go in one direction, so you shouldn't end up with any deadlocks. Yeah, you'll just end up with it maybe taking a bit longer, which what you're doing is testing performance. So as long as it doesn't take so much longer that it affects the shape of the numbers that you're seeing, then I think you're okay.
Yeah, but what I could do is just work with injection, and if I want to test the performance, I inject nothing, no logger, then I have the pure performance. If I see there is a problem,
right,
I can inject the logger.
Yep.
And then I can, and then it's normal that it will take a little bit longer, but then I keep open this possibility.
Yep.
Because I don't like to throw away code and then later reinvent it, and
right.
It's nothing is difficult. Once you get to it, you better have it.
Yep.
All right. Let me see whether there was anything else I wrote down. The Merkle Trees, we had all the problems. I think on my side that was my list of questions.
Very good.
So.
Yeah. Well, as you might imagine, I have seen a couple of other things that I would like to optimize. So, so I do have those threads kind of running in the background. One of those might be important to you coming up soon, and that is since I discovered that that latency is a significant source of performance degradation. The save algorithm does several different queries. They are not multiplicative. Each one is, here's a set of data. Go ahead and insert these fact types. Okay, I got those. Now insert these roles. Okay, I got those. Insert these facts. Insert these edges. Insert these ancestors. I believe that I can make a more complicated SQL statement. Maybe even turn it into a store procedure. I don't know if I want to go that far, but certainly make a more complicated SQL statement that says, here's all the information about some facts. Now you insert the the facts, edges, and ancestors. I can at least group those three together.
Yeah, you have just one round trip, and everything is set off.
Yeah. Yeah, okay. So that might speed up the saves, because right now the fastest that I can get a save on the managed Postgres database is about 300 milliseconds, which is noticeable to a human who is just hitting the vote button. It's like, yep, I would take that course if it was offered, and if they don't see that button, There he is.
Yeah. Discord is playing up again.
Yeah. But yeah, if they don't see that button light up within half a second, they're going to hit it again, and so you get these duplicate votes. So I've already modified the application to eliminate the duplicate votes on query, so you're not shown, that this person voted 3 times for the same idea. But yeah, it'd be better to get a more immediate response, which I can do by just using the local browser database, because then it only waits until it gets committed to that local database before showing the response. But before turning that on, I really would like to optimize that save path and see if I can get it down to less than, maybe less than 100 milliseconds. That'd be good.
Well, every time we can gain a little bit there, why not?
Yeah.
It improves the performance feeling for the users. Great, and then 3.1 is
I think so. I'm thinking I'm kind of targeting 3.1 for when the server can accept a projection.
Yeah.
And that will be the version that I want Jinaga.net to target.
That will be nice. All right, then I'm gonna try to make some time today to continue.
Excellent.
But it starts already bad because I still have to call back a customer. For who he called me 15 minutes before the start of this meeting.
Oh my.
And I say, I don't remember. I have to go and check my source code.
Ah.
So I said I will call you back later. So I'm gonna do that first, and then I dive into Jinaga, because otherwise next week I have to say again I made no progress. And I hate to say that. Yeah. Okay.
That's all right. We'll get there.
Yeah. Michael, thank you very much.
Thank you so much, sir.
See you next week.
Indeed. I will be here.
Okay. See you. Bye-bye.